I'd like to finish up this introductory section involving functions by talking about equations for straight lines, distances, equations for circles and how to manipulate them, and inverse functions today. Probably the format that most people remember when they think about straight lines from college algebra is this. You can describe a straight line by an equation that looks like this. The up and down y coordinate is some constant number m, the slope of the straight line, times x, plus a number b, which eventually is going to represent the y-intercept to us. For example, if you had y equals 3x plus 1, if x was 0, then obviously y would be 1. So that would be your y-intercept here. The slope being equal to 3 means that rise over run has to be 3. So I have to move up and down 3 units if I move 1 unit sideways, so that rise over run comes up 3 over 1, which is 3. Or obviously you could have done 6 over 2 or any other fraction of up and down over horizontal where the ratio came up equal to 3. But I'm just going to do it this way because that's as simple as a thing I can think of. If you draw in the straight line that connects those 2 points, you get, up to my horrifically bad ability to draw, this picture. Or if you want, you can put this on the calculator as we've done before. I'm going to put in y equals 3x plus 1. And to start with, we'll put it on the standard viewing window, although we'll adjust things also. So I'll press zoom and make choice number 6. And I get a straight line. It's a little bit difficult to see what's going on in the middle of the picture. So I'm going to adjust the X and Y range. I'm going to press zoom. And then one of the choices is zoom in, which is choice number 2, and then press enter. This shows me a close-up of what's going on close to the place where the X and Y axes cross. Also, I can select an X and figure out what the Y is on the graph to go with it. This way, I can press this button, which is the trace button, and then I can type an X value, for instance, X equals 0, and then press enter. And it tells me that on this graph, when X is 0, Y is equal to 1, which, as we know, is correct. If I move 1 unit sideways and 3 up, I'm off the top of the screen here. So I'll go back to the standard viewing window to look at that. I'm going to press trace. This time I'm going to make X equal to 1. And again, you have to press enter. And this tells me that when X is 1, Y is 4, as it should be. As we go along, I'll introduce little calculator techniques in case you don't know them already. I want to look at this situation. You've got a straight line. It passes through the point 1, 2. That is to say, X is 1 and Y is 2. It also passes through the point where X is 5 and Y is 12. I want to find an equation that describes the straight line. This is a little bit awkward because I haven't explicitly told you either the slope or the y-intercept. We'll be able to figure the slope out easily enough. As for the y-intercept, this is a little awkward, but we'll be able to figure it out anyway. But this is not the best way to do this problem. I've got to figure out the slope. I'll call one of my points 1, 2. I'll call that x1, y1. The other one will be x2, y2. And if you calculate the difference of y2 minus y1, over x2 minus x1. That ends up being 5/2 after all the simplification has been done. So I know what the m is now. Y is 5/2 times x plus b, where the b tells me where the y-intercept is, and I still don't know what the b is. At this stage, I have two facts that I could use to try to figure this out. Firstly, I know that this point 1, 2 is supposed to be on the line. That is to say, if x was equal to 1, y is supposed to come up equal to 2 in this formula. Also, when x is 5, y is supposed to be 12. So if I make the x equal to 5, the y needs to come up equal to 12. I can use either one of these two different ideas. It shouldn't make any difference because if you have two distinct points, there's only one straight line that goes between them. We'll see about that. Firstly, I'm going to use this fact that 1, 2 is supposed to be on the line, which says 2 has to be what I get when I stick x equal 1 into this formula. If you rearrange stuff, it turns out that b has to be negative 1/2. So strictly speaking, if you wanted to be picky about it, you would say that y is equal to 5/2 x plus negative 1/2. But of course, most people would just write that as y equals 5/2 x minus 1/2. Now, what if we had used the other fact? 12 is supposed to be the y number when x is equal to 5. So 12 needs to be 5/2 times x, which is 5, plus b. And once again, you can rearrange all this stuff. And when the dust finally settles, you get b equal negative 1/2, which naturally is the same thing that you got over here for the y-intercept. It has to be like that because otherwise you would have a straight line that had two different y-intercepts, and that's clearly impossible. If we want to do a sanity check on this, let's draw the graph on the calculator. So I'm going to get rid of what I used to have by pressing the clear key, that is. 5/2 is 2.5. Y is going to be 2.5x minus 1/2, which is 0.5. Put that on the standard viewing window. And then even though it's a little hard to see what's going on in the middle of the picture, we'll just use the trace feature anyway. I'll say trace. It wants to know an x value, so I'll tell it that x equals 1, and I find out that the y coordinate is equal to 2, which is what it's supposed to be. Also, press the trace button, make x equal to 5, and press enter, and you find out that when x is 5, y is 12, just like it's supposed to be. There is only one straight line that passes through any two different points, so this must be the right answer. I know that for sure now. A frequently more convenient way of writing this sort of thing is called the slope-intercept form, except that it isn't. It's called the point-slope form of the equation for the straight line. And it works this way. If I know a straight line and it has slope equal to m, and I know that it passes through a given point, x0, y0, then I can just write down the equation for the line as y minus y0 equals m times x minus x0. I want to rework the problem that we worked just previously to make sure that I get the same answer. First, we'll need to calculate the slope, but we've already done this in the previous problem, and like before, the slope works out to be 5/2. Then I've got a choice to make. I have 2 points. I could use either one of them to write down this point-slope form of the equation of the line. In version number Roman numeral 1, I'm going to use the point x equal 1, y equal 2 for my given point. So the equation for my straight line allegedly is y minus y0, y minus 2 equals 5/2 multiplied by x minus x0, which is x equal to 1 here. On the other hand, having figured out that the slope is 5/2, I could have used that other point, x equal 5, y equal 12, for my x0, y0 point. My equation for my straight line would be y minus 12 equals 5/2 times x minus 5. And there's a problem, an apparent problem here. This is supposed to represent the straight line I'm interested in, and so is that one, but they don't obviously mean the same thing. It turns out that they do, but it isn't obvious that they do. In order to see that, we're going to reduce both of them down into the actual slope-intercept form. So in the first version of your equation, 5/2 multiplied by the quantity x minus 1 is 5/2 times x minus 5/2 times 1. That's the distributive law. Then I want to get the y by itself. So here, I'm going to add 2 to both sides. And after everything settles down, y equals 5/2 times x minus 1/2, which, if you remember, is the same answer we got using the y equal mx plus b format to start with. On the other hand, if you look at the second version of this line, 5/2 times x minus 5 is 5/2 times x minus 5/2 times 5 is 25/2. Then you've got to add 12 to both sides, which is 24 over 2. And when you combine all the fractions, you find out that this equation means the same thing as y equals 5/2 x minus 1/2, which is the same thing that this equation meant after you got done simplifying it down into this format. So these two equations, they don't look the same, but they mean the same thing. They secretly are the same. It just didn't look like that at the beginning. The last remaining form is called the general form of the equation for a straight line. The premise is that there are numbers capital A, capital B, and capital C, and that the equation ax plus by equals c describes a straight line. You might want to take note that the b in this equation is not the same b that was in y equals mx plus b. It doesn't mean the same thing. As an example of this, if you look at 3x plus 2y equals 6, so that the a is 3, the b is 2, and the c is 6, if you wanted to, you could reduce this down into a more familiar format. Either think of subtracting 3x from both sides or adding negative 3x. You'll find that 2y is negative 3x plus 6. Divide through by 2, y is negative 3/2 x plus 6 over 2, which is y equals negative 3/2 x plus 3, which is the equation for a straight line with y-intercept at 3 and slope equal to negative 3/2. So really, this is just another format that you can write these kinds of equations in. Since we know that anything that looks like that is going to have a graph that's a straight line, I only need to identify 2 points on that graph to know what it looks like. For example, we'll think about this 3x plus 2y equals 6. I'm going to look for an x-intercept. That's going to be a place where you're on the y-axis, where you're on the x-axis, that is, so that y is 0. In this formula, if y is 0, that just says that 3x has to be 6, which tells me that x is 2. So this graph is going to cut across the x-axis at this spot where x is 2 here. On the other hand, if I try to make x equal to 0 so that I'm on the y-axis, when x is 0, our equation just says 2y equals 6, which obviously means y equals 3, and my y-intercept has now been located also. Since this is a straight line, just draw a straight line that connects those 2 points, and you have a good picture of what the graph looks like. 2 special cases are worth mentioning. If you have a horizontal line, all of the y coordinates are going to be the same, even though the x coordinates can be different. So think of looking at the point where x is 3 and y is 5, and the point where x is 10 and y is 5. If you calculate the slope, the difference of the y coordinates comes up 0, the number on the bottom comes up 7, and 0 divided by a non-zero number is 0. So the slope equals 0 in this case. If you wanted to, you could literally write this as y equals 0 times x plus 5. That's a little silly because the first term is always 0 and doesn't contribute anything no matter what the x is. So most people would just write this equation as y equals 5. The other way around is when the y variables can change, but the x is always a constant. If you try to calculate the difference of the y's divided by the difference of the x's here, you get 5 divided by 0, which, unlike what happened in the horizontal case, doesn't give you an answer. It's not that the slope is 0. There is no number that I can call the slope. People have a tendency not to believe me, so in this first bit, 0 divided by 7 is a perfectly good number. It's 0. In the second example, 5 divided by 0, the calculator disapproves of that. There is no such thing. So when I say there's no slope on a vertical line, I don't mean that the slope is 0. I mean, I can't cook up a number to call the slope. I have to make a little comment about distances. Distances are not negative, not ever. And the only way that the distance between 2 points on a number line can be 0 is if they're the same number. If I have 2 numbers on a number line, like for instance 2 and 5, and I want to know the distance along the number line, that's easy to figure out. All you do is take the bigger number minus the smaller number. 5 minus 2, which is 3 units of distance here. To have a sanity check, 1, 2, 3. So this is correct. If somebody put down 2 numbers, A and B, but they didn't tell you which one was bigger, if I knew that the B was bigger than the A was, the distance would be B minus A, just like the 5 minus 2. If I knew that the A were bigger, then it would be A minus B, though. One of these numbers is the negative of the other one. So, for example, if A were 7 and B were 3, the other way around, if A was 3 and B was 7, the distance would be B minus A, which is 4. But if you calculated it in the other order, you would get negative 4, which is no good because distances are not negative. It's almost right, though. It's right, except that it has the wrong sign on it. To remove any conceivable unwanted minus sign on this, we're just going to say that the distance from A to B on the number line is the absolute value of A minus B. In this way, we will get rid of any negative signs that we don't want, and we don't have to worry about which one is bigger. So the distance from 3 to 5, if I just calculated 3 minus 5, that would be wrong. That would give me a negative answer. But if I calculate the absolute value of 3 minus 5, that's absolute value of negative 2, which is just 2. If I do the distance from 9 to 6, if I literally calculate it as absolute 9 minus 6, that would be absolute value of 3, which is 3. But even if you got the order backwards, absolute 5 minus 3 is absolute 2, which is 2, and absolute 6 minus 9 is absolute negative 3, which is 3. I would still get the same answers. This is a minor point, but it will trip us up sometimes if we're not careful about it. So I wanted to at least mention that. The preceding fact is related to something that does trip people up very much sometimes. If you looked at the principal square root of x squared, is that or isn't it always equal to x? You would think that the answer is obviously yes, and why would anyone even think of asking such a thing? For example, if x was 5, what is principal square root of x squared? That would be principal square root of 25. And we said that when we use that radical sign, we're talking about the square root that isn't negative. So out of the two choices, negative 5 and positive 5, you would write down the 5 instead. So far, things are the way you think they would be. What if x was negative 5? When you multiply negative 5 by itself, you get 25 again. So what I'm going to have to calculate is principal square root of 25. And we just said a minute ago that that's 5. So this is 5. And that is not x. It's the negative of x. So the way this is going to work is, if x is not negative, like 5 for instance, then radical x squared is just x and you can be done with it. If x is negative though, that doesn't work, and radical x squared is the absolute value of x, not just x by itself. And this goes back to that statement that the radical symbol here, the principal square root, never hands you back a negative answer. This will trip you up on various issues if you're not careful about it. I want to think about distances in a two-dimensional plane. The way this is going to work is it goes all the way back to Pythagoras and his theorem about right triangles. If you have a right triangle, the long side, the hypotenuse, is the side opposite the right angle, and I'll call the lengths of the other two sides A and B. I want to use the Pythagorean theorem, c squared equals a squared plus b squared, to figure out how to do distances in a two-dimensional plane. So imagine that you've got 2 points. One of them, this one, I'm going to call x1, y1, and this one I'm going to call x2, y2. The distance between them, I'm going to call that distance d for distance, and I want to figure out a formula for d in terms of the 2 points' coordinates. So here's what you do. Start at the bottom and draw in a line that's parallel to the x-axis. Start at the top and draw in a line that's parallel to the y-axis. Now, the x-axis and the y-axis are at right angles to each other, so this angle must be a 90-degree angle. On the other hand, if I use the x-axis like a ruler, the distance horizontally from this point to that point, the way I've got it drawn, I'm going to write it as x2 minus x1. Although, if the bottom point were further to the right than the other point, it would be x1 minus x2. Really, I ought to say absolute value here, but I'm going to square this distance in a minute anyhow, so if I've got its sign wrong, it will fix itself. Likewise, use the y-axis like a ruler, and pretending that y2 is the bigger of the two numbers, this distance is y2 minus y1. What the Pythagorean theorem says is the square of the distance that I'm after is this distance squared plus that distance squared. So I'm just going to write that fact down. Distances are not negative, so I don't have to worry about any kind of square root of 9 being 3 or negative 3. We just want the one that's not negative. So the actual distance is the square root of, take the difference of the x's squared, take the difference of the y's squared, add them together, do the square root, and there's your distance. Before we say anything else, I need to make a comment about that. There is no simplification of this formula that will result in something involving only the x stuff and other stuff only involving the y stuff. You cannot break this up into two different square roots and simplify it like that. The arithmetic doesn't work if you try to do that. The reason I mention that is I've seen people do that many times, but that's not right. Let's think about a little bit of geometry. If you go all the way back to the ancient Greeks, they defined a circle this way. A circle is a set of all points that are the same distance, a common distance, from a certain fixed point in the plane. This common distance is the radius of the circle. Since it's a number, a distance, we'll make up a letter to call it by. We'll call it r for radius. The certain fixed point is the center of the circle. We describe points in the plane with pairs of numbers, x and y numbers. So this center, I'm going to make up a name for its x coordinate. I'll call it h, and the name of its y coordinate will be k. So what does it mean for the distance from a point, which I'll just generically think of as xy, to the point hk, the center, to always equal this r number? I'm literally going to write the distance formula down. The difference of the x coordinate squared, add in the difference of the y coordinate squared, take the square root of that, and you get the radius. That is a literal mathematical formula that means exactly the same thing as the distance from xy to hk is r. The is got turned into the equal sign. For this particular kind of situation, it's traditional to square both sides to get rid of the radical sign. So x minus h squared plus y minus k squared equals r squared is the equation of a circle with radius r with center at the point h comma k. If somebody wrote down something like that in front of you with actual numbers for the h, k, and r, you should take one look at it and tell them what the picture looks like. For example, say we've got a circle. The radius of the circle is 2 units, and the center of the circle is at x equal 5, y equal 3. Literally, writing down that equation that we just had on the previous page, x minus 5 squared plus y minus 3 squared equals 2 squared. Or if you think the 2 squared is a little awkward looking, go ahead and write it as 4. This is an equation that describes the circle that we're talking about. If you wanted to draw some points in, first, locate where the center of the circle is at. That's at x equal 5, y equal 3. And I want to draw in a bunch of points that are exactly 2 units away from that. so the distance is 2. Obviously, you can draw a lot of points in. My y-coordinate here is 3. If I lower it by 2, go straight down, I'll have this point, or starting at the center, go up by 2, or to the right by 2 units, or to the left, or off at any of a whole bunch of possible angles. I think it's pretty clear that if you were to somehow draw in all points that were exactly 2 units away from that center, you would have the circle that you're talking about. So if somebody asks you to write down an equation for this kind of circle, it's almost an insult to your intelligence. Something that's not an insult to your intelligence is draw such a circle on your calculator. There's going to be some problems with this. In the calculator, as we know it, everything has to look like y equals, and then stuff with x's in it. If you take the second semester calculus course, you'll find out that we can get around that and fix all the problems that we're about to see. But as far as it goes right now, we're going to draw this on the calculator. We're going to get poor results. We'll be able to fix at least part of it, but part of it's going to remain a problem. Oh, and it's worth mentioning that depending on the exact time at which your calculator was manufactured and the exact serial number ROM that you have, some calculators will have a problem and others won't. So you should check on yours to make sure. Anyway, I want to rig this up so that I can draw it on my calculator. Subtract x minus 5 squared from both sides, and you'll find out that y minus 3 squared is 4 minus the square of x minus 5. We could multiply x minus 5 squared out and simplify it and combine it with the 4, but it turns out that really doesn't help you any, so we won't be doing it. This says that y minus 3, well, it could be the principal square root of 4 minus x minus 5 squared, or it could be the negative of that. If I tell you that a number squared is 16, say, the number might be 4 or it might be negative 4. If this happens, add 3 to both sides, and you'll find out that y is 3 plus radical 4 minus x minus 5 squared. If it's the first choice, add 3 to both sides of this, and y is 3 minus radical 4 minus x minus 5 squared. Obviously, these y numbers are going to be smaller than these y numbers. So my circle is going to be described in 2 chunks. This is going to get a little awkward here, so just one moment. For y1, I want to put this in. So I'm going to have 3 plus the square root of 4 minus, open parentheses, x minus 5, close parentheses, squared. And then I have to close parentheses on the square root. Let me make sure I haven't made any typos there. Standard viewing window. Okay, we'll notice that we don't have objections to this already, but we'll see about that in a minute. The other one is this one. I'll put this in as y2. y2 is going to be 3 minus the square root of 4 minus, open parentheses, x minus 5, close parentheses, squared, and then close parentheses on the square root function. Put it on the standard viewing window. Well, there's a couple of things wrong with this picture. Number one, it's kind of elongated, and number two, there's gaps in the middle. But if there's anything to this at all, this somehow is the top half of the circle, and that's the bottom half. But obviously, there's some explaining to be done here. Firstly, why is it so elongated? If you look at the screen, there are more pixels this way than there are that way. This tends to introduce kind of an aspect bias to it, and it distorts the picture. In the zoom settings, there's a way in the zoom settings to tell it how to try to correct for that as much as it can. So I'm going to go into zoom settings, and one of them is number 5, Z square. When we press that one, what that's going to do is tell the calculator, I know I got more pixels sideways than I do up and down. Try to correct for it if you can. So push zoom number 5, and the picture that we get looks a little bit more like a piece of a circle, but there are these gaps on the side. I'm not going to make too big of a deal out of this at the moment, but what's happening is this. When you tell your calculator to draw a graph, it picks a bunch of little X numbers. It sticks them into the formula for a Y, Y1 or Y2 in this case, plots them, moves forward 1 pixel, and then tries to connect the next dot with a straight line segment. The problem here is that the steepness of that circle is getting real big as you get towards either the right end or the left end, and moving 1 pixel sideways moves you a lot of pixels down, and it skips some stuff. Some things that should get plotted on the screen don't get plotted at all. That's the origin of this pair of gaps here. There is no easy way to try to fix that. So I'm going to put this off until we talk about parametric equations in Calc 2 if you take it. It turns out to be easy enough to fix, but it's not something we want to talk about just yet. There are a couple of facts that I need to remind you of. If you add 2 numbers together and then square the result, what you get is the same thing as the square of the first number plus 2 times the first number times the second number plus the second number squared. And in a similar way, if you had a minus b and you wanted to square that, that always turns out to be a squared minus 2ab plus b squared. And I'm going to need these 2 facts in order to talk about completing the square. Oh, and if you don't believe these 2 facts, write a plus b multiplied by a plus b and do the FOIL method on it. You'll see that it's true. Suppose I had some number a, and all I know about a is a squared plus 6a. I happen to know that that's equal to 7. I'm looking at that a squared plus 6a, and I'm thinking about this. I want to think of a squared plus 6a as being a squared plus 2 times a times something. The something has to multiply together with 2 to give me this 6 here. So obviously the something is 3. It's half of the coefficient of the a to the first power term. So I'm going to take the 6 and cut it in half if I want to think of it that way. 6a is 2 times a times 3. So I'm thinking about this formula, and I'm thinking to myself, you know what? It's too bad that I don't have 3 squared added on, because then I'd have a squared plus 2 times a times 3 plus 3 squared, and that would be a perfect square. This is why we call this completing the square. Well, since I wish that were true, I'm going to stick an extra 9 in. Of course, there's a catch. I have to balance the books somehow. So I'm going to take this number and this number, which are equal to each other, and I'm going to add 9 to both of them, and the answers have to be equal. The reason that I want to do that is the thing over here is now a squared plus 2ab plus b squared, where b is equal to 3. That's the same thing as a plus b squared, to be specific, a plus 3 squared. So this business is a perfect square. It's a plus 3 squared. And over here, 7 plus 9 is 16. I've got a number. The name of this number is a plus 3. Don't know about the a yet, but I do know something about a plus 3. When you square it, you get 16. So that tells me something about a plus b. Excuse me, a plus 3, that is. If a plus 3 squared is 16, only two things can happen. A plus 3 might be 4, or a plus 3 might be negative 4. In the first case, subtract 3 from both sides, and you'll find out that the a has to be 1. In the second case, subtract 3 from both sides, and you find out that the a has to be negative 7. If you have a squared plus or minus a number times a, cut that number in half, square what you get, and add it in to get a perfect square. That's why this procedure is going to work. Our application of this, I'm just going to plop this equation down in front of you. X squared minus 8x plus y squared minus 2y is negative 3. And I want to know what that looks like. If you'll notice, I can regroup stuff. X squared minus 8x off by itself. Y squared plus 2y off by itself equals negative 3. And then what we're going to do is complete the square twice. I've got x squared minus 8x, and I'm thinking to myself, cut the 8 in half to get 4, square that, and add it. So I'm going to add 4 squared, both on the left side and the right side to keep things equal. Y squared minus 2y, half of 2 is 1. So I'm going to square that and add it in, both on this side and on that side. The two terms that involve the x and y are now perfect squares. This one is x minus 4 squared plus this one is y minus 1 squared, and this adds up to be 14, if I've done my arithmetic correctly. We had previously written down the equation for a circle with center at a certain point and a given radius. It was x minus h squared plus y minus k squared equals r squared. So just compare things. H has to be 4, k has to be 1. The center of this circle is going to be at 4, 1. Radius squared is 14. Since radius isn't negative, it's a distance, don't have to do the plus or minus thing. The radius is the non-negative square root of 14, principal square root of 14, if you prefer. The last thing I want to talk about today has to do with inverse functions. Before we start talking about that, I want to remind you of something. When you're looking at the graph of a function, the y-coordinate, or more generally the vertical coordinate, is the function value that goes with the horizontal, usually x coordinate for us. This is true for all functions, no matter what their name is. I'll probably end up saying this about 1 billion times before we're through, but it's an important point. Suppose you have a function f. Now, depending on what the f function does to its inputs, there may be another function g that undoes whatever f did. And what I mean by that is if we think of these things as procedures, I would take some input, feed it through the f function to get f of x, then take that number and feed it through the g function to get g of f of x. Usually that's going to be some big complicated mess, but it could be that there's a function g so that if you take any x that's legal to feed into f and do this procedure, you end up with the thing that you started off feeding into f in the first place. G would take an f of x and tell you what the x was that went with it. If there is such a g, and not all functions have such a g, but if there is, I'm going to make up a name for this function. Instead of calling it g, we're going to call it f inverse. And that's how you pronounce that, f inverse. And I don't mean the reciprocal of f, 1 over f or something. And I certainly don't mean f raised to the negative 1 power. If it exists, f inverse is the function that undoes whatever procedure f did to all of its x's. An insulting example, f of x is 3x. F inverse of x, I claim, is 1/3 x. Let's make sure that that's true. F of f inverse of x is an f value. It's going to be the f value that I get when I stick f inverse of x into the f procedure. Allegedly, f inverse of x is 1/3 times x, so I'll write that down. We are supposed to reinforce the function concept in this course, so this is as good a place to start as any. This little formula here means in language this: f is a ruler procedure, and the way you do f to a number is you multiply the number by 3. That's all it means. There's nothing deeper going on here. So I want to calculate an f number that's going to be 3 times whatever I'm feeding into the f function. That would be 3 times 1/3 times x, and the 3's cancel out and give me my x back again. So if I take x and I feed it through this process, get the answer 1/3 x, feed that through that process, which triples whatever this last process was handed, I always end up with the same thing I started with. That's what I mean when I say that this is an inverse function to that. Much less obviously, if f of x is 3x plus 1, which means the way you do the f process to a number is this: you triple the number, and then after you do that, add 1 to it. If f is that function, then I claim, without any justification, that f inverse x is the number x minus 1 divided by 3. Let's check that. I'm going to calculate f, evaluated at not x, but at f inverse of x. This is going to be an f value where the input is x minus 1 over 3. So I have to take f of x minus 1 over 3 to calculate this. How do you do f to something? You multiply the something by 3 and then later add 1 to that. So take the something, the x minus 1 over 3, multiply it by 3, and then add 1 to that. The 3's cancel out, and you end up with x minus 1 plus 1, which is x, just as I claimed it was. This function really is the undoer of that function, the inverse function to f. Generally speaking, how are we supposed to figure these things out? If I write down the equation y equals f of x, when you're on the graph of f, the y coordinate is the function value. Literally, that first equation describes the graph of f. Now, let's suppose that you have an inverse function. Suppose that one exists, like one of the examples we've looked at just now. If y and f of x are the same thing, when you take two numbers that are the same thing and do the same thing to both of them, you get the same answer. So y is the same thing as f of x. If I take those two numbers, which are the same, and I feed both of them into the f inverse function, I have to get the same answer. So f inverse of y has to be f inverse of f of x, but f inverse is supposed to be the function that undoes whatever f did. So I'm going to end up with an x over here. If I'm looking at the graph of f, then this is equivalent to x equals f inverse of y. That's the same thing as y equals f inverse of x, except the x and the y have been interchanged, which you may remember means you've done a mirror image across the line y equal x. I'm not going to go there today. So I could write this formula down. If you interchange the x and the y, you're supposed to get something that represents the graph of f inverse. And when you're on the graph of a function, the function value is the y coordinate. So if I can solve for y in terms of x, then I'll have a formula for my f inverse of x. It sounds much worse than it actually is. Suppose f of x is 6x plus 5. I want to find a formula for the inverse function. If I write down the equation y equals 6x plus 5, that's literally y equals f of x. That represents the graph of function f. If you interchange the x and the y coordinates, that becomes x equals 6y plus 5. Morally speaking, that is equivalent to y equals f inverse of x. So if I can solve this equation for y in terms of x, I claim that's going to be f inverse at x. And that's easy. Subtract 5 from both sides, divide both sides by 6. This equation, which philosophically means the same thing as y equals f inverse of x, is the same as y equals x minus 5 over 6. This has to be f inverse of x. So I claim that f inverse of x is the number x minus 5 divided by 6. Let's do a sanity check. Using these formulas that we've got, if I calculate f of f inverse of x, this is an f value, the input is f inverse x, which is x minus 5 over 6. The way you do f to a number is you multiply the number by 6 and then later add 5. And as usual, the 6's here cancel out. X minus 5 plus 5 is x. So if we can do the algebra, we can actually find formulas for inverse functions. We can find formulas for f inverse x. Usually, it's not easy enough to do that, but in some cases we can. And of course, there's the inevitable bad news. Not every function has an inverse function. Think of f of x equals x squared. The graph of that is y equals f of x, y equal x squared, which is our familiar parabola shape. trying to carry this plan out that we had a minute ago, interchange the x and the y. So it's now not y equals x squared, but x equals y squared. If you tell me the y number, I'll tell you what the x number is to go with it. Things that were vertical are now horizontal, and vice versa. So we've done this mirror image reflection across the line y equal x. On the original picture, x could be anything, but y had to be 0 or bigger. When you interchange that, it's now that the x has to be 0 or bigger, and the y can be anything. But there's real bad news about this. This picture violates the vertical line test because the original graph could be touched with a horizontal line in more than one place. This is not the graph of a function. So strictly speaking, the squaring function doesn't have an inverse function. On the other hand, we can kind of sort of fix this up by restricting the x's that you're allowed to look at in the original picture. So what we're going to do is, we're not going to let you look in the original picture on the graph of y equal x squared at any x that is negative. X can only be 0 or positive, so I'm only looking at the right-hand part of the parabola. Now everything is fine. No horizontal line touches that more than once. X and y are both positive on this picture, so when I interchange them, x and y are still going to be both positive, meaning that the part that remains when I interchange the x and the y is going to look like that. It's the top half of that sideways opening parabola that we had, and this is perfectly okay. This passes the vertical line test. This function has a name, and the name is principal square root. Principal square root can never give you a negative answer back. Also, you cannot put negative numbers into it. And in case you don't believe me still, y equals square root of x. Put it on the standard viewing window. I don't get anything when x is negative, and I get the top half of that parabola when x is 0 or positive. If you zoom in, the curvature is a little bit more obvious and clear there. Hopefully this reminds you of most of the stuff we're going to need from algebra. I've got a little bit more to do in the second chapter of the textbook, and after that we'll start talking about what we're really interested in, which is exponential and logarithmic functions, trigonometric functions, and various applications. In the meantime, have a good day, and we'll talk about more stuff in the next discussion.